Hello everyone, I am Suraj Badnekar, Assistant Professor of Mathematics at Ganpat Parsikar College of Education, and I welcome you all to module number 10 of this elementary course on combinatorics titled The Binomial Theorem Part 2. In this module, we shall study some more identities associated with the binomial theorem which we have defined in the previous module. To kick things off, we have something called Vandermon's identity, which says that for all positive integers n, and k, of course, I need to have the combinations defined, well defined. We have n plus n ck equals the sum running from I to k, nci into nck minus I. Now the proof of this identity is fairly simple. If you look at the left hand side, I am creating k element subsets from a set of n plus n elements, and on the right hand side n and m have been separated. So that is the whole idea behind this. I need to split my set into a set of n elements and a set of n elements. Okay, so let me start with the proof. The left hand side counts the number of k element subsets of a set of m plus n elements. That is n plus m choose k. This is fairly straightforward. Right? Suppose we split this set into two. That is a set of m elements and a set of n elements. Of course, both disjoint. There should be nothing common to both these sets. Again, I need to select a subset containing k elements. So suppose I choose I elements from m, it means that I need to select the remaining k minus I elements from m. That's it. This is the idea of the proof. To form a k element subset, we can choose I elements from the m element set, and the remaining k minus I elements from the n element set. Therefore, the number of ways of producing a k element set would simply be the sum running from I to k, nci, nck minus I. Therefore, we must have n plus m ck equals summation k goes from summation I goes from 0 to k MCI NCK minus I, and this completes the proof of the theorem. So to summarize, we simply divide our set into two parts: a set containing m elements and a set containing n elements. Remember, both of them have to be disjoint. You cannot have anything in common to both of them. Now to form a k element subset, if I choose I elements from the first set, obviously I need to choose the remaining k minus I elements from the second set. So this is how I get the proof of the identity. Alright. Now this one seems pretty long but can be proved easily using Pascal's identity. If you start with the right hand side, which is n plus 1 c k plus 1. This can be done in nck plus nck plus 1 ways. This comes from Pascal's identity. Keep NCK as it is. Apply this same theorem, apply Pascal's identity again on NCK plus 1. That will give me n minus 1 CK plus n minus 1 C K minus 1. This is nothing but Pascal's identity on a set of n elements, in which we consider a specific person A to be either present in the set or not present in the set. Now, on the last term in this equation, I apply Pascal's identity once again. So I get nck plus n minus 1 ck plus, I shall now get n minus 2 ck plus n minus 2 ck plus 1. Continuing in a similar manner, we will get nck plus n minus 1 ck plus n minus 2 ck plus so on. The last term that we will be left with is k plus 1 ck plus 1. But k plus 1 ck plus 1 is nothing but k ck. Both of them are equal to 1. This is something you know from basic properties of NCR. So I can simply replace k plus 1 c k plus 1 with k c k, and that is how I get the left hand side of my identity, which is k c k plus k plus 1 c. Since we know that k plus 1 c k plus 1 is simply equal to k c k, I will replace k plus 1 c k plus 1 with k c k in my expression, and this is how I get the left hand side of my identity. So I simply use Pascal's identity for every single new term which appears in the equation. Moving on to the next theorem. For all non-negative integers k and n such that k is less than equal to n minus 1 upon 2, the inequality nck less than equal to nck plus 1 holds. Furthermore, equality holds if and only if n equals to k plus 1. Now, what happens in this case is, say you're looking at the number of subsets you can form using a set of 5 elements. So we have 5C0, 5C1, 5C2, 5C3, 5C4 and 5C5. Now when I say k is less than equal to n minus 1 by 2, I am talking about k being in the earlier half of these terms. So I am talking about k equal to 0, k equal to 1, k equal to 2. And what this theorem says is, nck will always be less than or equal to nck plus 1. So 5c0 will be less than 5c1, will be less than 5c2, or equal to, whatever. But after a point, we will start reversing the sign of inequality, meaning the values of nck will keep on increasing will hit a peak value somewhere in the middle and then start decreasing as you move towards NCN. So if you know 5C2 is equal to 5C3 and then 5C3 is greater than 5C2 and 5C2 is greater than 5C3. Okay, so this theorem is meant for the first half of this string of combinations. So let us start with the proof. I have k less than equal to n minus 1 over 2. This implies 2k is less than equal to n minus 1 or k plus k is less than equal to n minus 1. Moving that minus 1 to the left and one of the k's to the right, I get k plus 1 is less than equal to n minus k, which implies 1 upon n minus k is less than equal to 1 upon k plus 1. I have simply taken the reciprocals on both sides, which reverses my inequality. Now, I will multiply the numerator by n factorial and the denominator by n minus k minus 1 factorial times k factorial. So I get n factorial upon n minus k times n minus k minus 1 factorial times k factorial is less than or equal to n factorial upon k plus 1 n minus k minus 1 factorial times k factorial. On the left hand side in the denominator, if you notice, n minus k times n minus k minus 1 factorial is simply n minus k factorial. And I have k factorial as it is in the denominator. On the right hand side, k plus 1 times k factorial is k plus 1 factorial. And I shall keep n minus k minus 1 factorial as it is. The left hand side, if you observe, is simply nck, and the right hand side is nck plus 1. And this completes the proof of the inequality. Now, in the inequality, it is further stated that equality holds if and only if n is equal to 2k plus 1. Which is quite obvious, because if n is equal to 2k plus 1, then I will have n minus 1 upon 2 is equal to k, which is actually the starting step of my proof, but with an equal to sign. So nothing changes at all in the proof except for the inequality sign. The inequality becomes equality in this case. Equality holds in case of n being equal to 2k plus 1 or k being equal to n minus 1 over. So that completes the proof of the identity. Let us now move on to the last proof under this module. Which says that for any positive integer n, summation k goes from 0 to n, 2 raised to k, n c k minus 1 raised to n minus k is equal to 1. Again, this is something which can be proved using the substitution method which we tried in the previous module. So what I shall do here is consider the expression for binomial theorem first. from the binomial theorem. I have x plus 5 the whole raised to n equals summation k goes from 0 to n ck x raised to k y raised to n minus k. Since I need 1 on the right hand side, it is ideal that we put x equal to 2 and y equal to minus 1 and see what we get. Therefore, the left hand side now becomes 2 minus 1 raised to n, which is equal to summation k goes from 0 to n ck 2 raised to k minus 1 raised to n minus k. The left hand side is simply 1 raised to n, which is a finite number, and hence it will be equal to 1. And the summation remains the same. There is no need to alter anything over here. And I get the required result. So that is it for this module.